So we're going to continue to work with identities. We're going to start with the basic identities, the ones that are on the formula sheet, and we're going to use them to prove other identities. So as it says, we're going to prove trig identities algebraically. We'll understand the difference between verifying and proving an identity, and show that verifying that the two sides of a potential identity are equal for a given value is insufficient to prove the identity. So, in this lesson, we will verify and prove more complex trig identities using the skills that we have learned from the previous lesson. Some useful steps or hints when trying to prove a trig identity are listed below. The one thing you have to remember is you are not allowed to move terms from one side to the other. Right? You can only do that if you have an equation. If you have an equal sign in between two expressions, you're told that they are equal to each other. Then you are allowed to do things to both sides. You're allowed to add and subtract values to both sides. You're allowed to multiply and divide both sides by the same value. You're allowed to take the square root of both sides or square both sides. You can do all those things if you know that the two sides are equal. The point of this lesson, and we'll do some more of this next class as well, is to show that the two sides are equal. You cannot assume that they are. You have to show that they are equal. So we're not dealing with equations, we're dealing with what's known as an identity. We want to know whether it's true or not. So, some helpful hints that we can use. Usually you'll begin with the more complex side. If possible, use known identities given on the formula sheet. Right? If you have any squares, look to those Pythagorean identities. If necessary, change all trig ratios to sine or cosine. So really, the first thing you're going to look at when you're looking at an expression, an identity, if there are no powers, put everything in terms of sine and cos. That'll be our first step always. If there are powers, especially if there's squares, look to the Pythagorean identities. Okay? So that's always going to be like our first step. Sometimes, though, you might have to factor. So if you have powers, especially ones greater than 2, that means you're going to have to factor. If there is a sum or difference of fractions, write as a single fraction. So what that's talking about, sometimes you got to get a common denominator to combine two rational expressions that involve trigonometric identities. You have to get a common denominator. So we'll see examples like that. And occasionally you'll need to multiply the numerator or denominator of a fraction by its conjugate. So we'll look at examples where that comes in as well. Okay? But we look at example 1. Consider that statement. 1 over cos x minus cos x is equal to sine x tan x. That's a statement. Okay? We are going to prove that it is an identity. Prove that it is true. You can't assume that it is. The whole point of these exercises is proving that it is. Now, you can prove that the statement is true for a specific angle. In this case here, it wants us to prove that the statement is true when x equals pi on 3. So we'll let x equal pi on 3 in the statement. So you'll have 1 over the cosine of pi on 3 minus the cosine of pi on 3. That's the left side. The right side is sine of pi on 3 times the tangent of pi on 3. So, to get out what these values are, pi on 3 is on the unit circle. Okay, it's about right there. And the coordinates there are 1/2, comma, root 3 over 2. We saw that the tangent was root 3. Again, that is derived by dividing sine by cos. Root 3 over 2 divided by 1/2. We did all this when we talked about the unit circle. So, the cosine of pi on 3, remember cosine is the x value. That's 1/2. So it's going to be 1 over 1/2. minus the cosine of pi on 3, which is still a half. And 1 divided by a half is the same as 1 multiplied by the reciprocal of a half, 1 times 2 over 1. So it's going to be 2 take away a half, which is 1.5 or 3 over 2. So that's what we get for the left side of that statement when x is pi on 3. The right side, the sine of pi on 3 is root 3 over 2 times the tangent of pi on 3, which is root 3 or root 3 over 1. Root 3 times root 3 is just 3 over 2 times 1. Get the same number, 3 halves. This shows that this statement is true for a specific angle. Okay, they told us to use pi on 3, and you could use almost any angle that's on the unit circle. You can use any angle you want, but at least when we're dealing with angles on the unit circle, we're dealing with exact values. Okay? And as I said, you can use almost any angle because when we get down to part D, it's going to talk about the restrictions in terms of x. What angles could not be used here? And we'll see what they are and why. But before we get there, looking at question B. Use a graphing calculator to show that the statement is probably an identity. So what this means, if we take our graphing calculator and we put both equations or both statements in there, the two graphs should be the same. So y1 would be the left side, the left statement. I'm going to use brackets to keep 1 divided by cosine x together as a term. So I close the bracket on the x, I close the bracket on the term, minus cosine of x. So I put the left side of the statement in y1. I'll put the right side in y2, which is sine x times tangent of x. Let's check the mode. Right now I'm in degree mode, and that's fine. I can stay in degree mode if I want. I just have to make sure my windows reflect that. So my x min, I'm going to go from negative 360 degrees up to positive 360 degrees and a scale of 90. Remember when we looked at the graph of sine and cos and tan? Sine and cos went up to 1 and down to negative 1. So if we were only graphing sine and cos, we really only have to go up to positive 1 on the y-axis and down to negative 1. But then we saw that the graph of tangent x went up and down forever. And there is a tan x in this statement. There's also a reciprocal function because 1 over cos x is the same as secant x. Okay. So we're not really sure what our y windows should be, and because of that, I'm going to leave them from negative 10 to positive 10 on both axes. So when I hit graph now, it'll graph y1 first, and then really fast, it'll graph y2. And it should be over top of y1. And so on this calculator, you'll see different color for the second equation. So when I hit graph, it's going to happen fast. There's the first one, and the second one is drawn right over top of it. So what this shows us, it shows us that this statement is probably an identity. And we use the word probably because this only shows that the two graphs are the same between the windows that we chose, between negative 360 and positive 360 degrees. It is possible there's a spot somewhere outside of that domain where the two graphs are not the same. We have no way of really knowing because we can't put an x minimum of negative infinity and an x maximum of positive infinity in here. And if we did, the graph would be so squished together, it would be really difficult to even see the graphs. So you can show that the statement is probably an identity by using a graphing calculator. You can show that the statement is an identity for certain values of x, like we did in part A, but it doesn't mean that it is an identity for all values of x. To do that, we do or use an algebraic approach, which is what part C is asking us to do. use an algebraic approach in order to prove that the statement is an identity. So this is what we're going to be focusing on for the next couple classes. Using known identities to prove that other statements are also identities. Okay? And we follow through those lists of hints that we were given. If there's any powers, you look to those Pythagorean identities. If there aren't any powers, normally you're going to put everything in terms of sine and cos. Sometimes you might have to get a common denominator to combine two terms. Sometimes. Okay? Sometimes you might have to factor. And sometimes you might have to multiply top and bottom by a conjugate. So those are the list of the hints that we're going to use. And I'm not going to lie to you. I mean, some of these you're going to have a bit of difficulty getting them. It's not that they're hard, it's just that maybe you're not as persistent as you should be. Because as we show you how to do each one, usually most of them can be done in 2 or 3 very simple steps. And when you see it's done, you're going to say, oh, Jesus, that was easy. And that's true. Most of them are. You need to try something, and if it doesn't work, you try something else. You have to be persistent. When I was in university, I took a course called Euclidean Geometry. We had to do these massive proofs. And I will compare that to this, because you'd sit there, or I would sit there, and I would try and figure it out, and I'd try something, it wouldn't work. I'd try something else, it wouldn't work. Sometimes I was living in Edmonton, go across the street to 7-Eleven, get a slushie, come back, try something else. I'm serious. Try something else. If it doesn't work, you try something else. And eventually, I got them. Okay? Considerably more steps than what you're going to have to do these. But that's the key. Don't give up. Some of them look like they're real beasts. And in many cases, the one that looks like they're going to be the hardest can actually be done the easiest. Use those hints that you were given. Right? If there's no powers, put everything in terms of sine and cos. If there's powers, look to those Pythagorean identities. If there's powers greater than 2, because the Pythagorean identities all involve powers of 2, if there's powers greater than 2, you're going to have to factor. And there will be some examples, and we'll see them, where you're going to multiply top and bottom by a conjugate. Try something. If it doesn't work, you try something else. Most of them can be done in 2 or 3 simple steps, and it's true. I'll show you how you do them, and you'll say, well, geez, that was easy. Most of them are. Okay? Just don't give up. Keep trying. But look to those hints. Okay. So, question C. Prove using an algebraic approach. So if we start with the original statement, the left side is 1 over cos x minus cos x, and that should equal sine x tan x. We need to show that the two are equal. So what we're going to do is we're going to get the same expression on both sides. That'll show that the two are equal. So in this case, if I work down the left side, I've got 2 terms. I've got 1 over cos x minus cos x, which is cos x over 1. If I want to combine those two into the same statement, I need to get a common denominator. I've got one fraction minus another fraction. To combine fractions by addition and subtraction, you need a common denominator. So my common denominator here would be cosine x. The first term already has a denominator of cosine x, so the numerator doesn't change, but the second term doesn't. To make this one become a cosine of x, you'd have to multiply top and bottom by cosine of x. Cos x times cos x is cos squared x. So when we get a common denominator, we combine those two expressions into one. We get 1 minus cos squared x over cosine x. What does 1 minus cos squared x equal? What can I replace that 1 minus cos squared x with? Huh? Who said back there? Why? Why? Pardon? Well, it's a variation of one of our identities. Our Pythagorean identity says that sine squared theta plus cos squared theta equals 1. And we said that you can use variations of this. In this case, if you get sine squared x by itself by subtracting cos squared x or theta from both sides, that's why 1 minus cos squared theta equals sine squared theta from the Pythagorean identity. I'm going to use this one lots. The Pythagorean identity, especially that original one, sine squared theta plus cos squared theta equals 1, I'm going to use that one lots, which we are here because 1 minus cos squared theta is equal to sine squared theta, or x, over cosine of x. So on the right side, you've got sine x times tan x. Remember we said that if there are no powers, quite often you're going to put everything in terms of sine and cos. I'm going to write tangent as sine x over cos x. The factor on the left is sine x, or sine x over 1. I change the tan x to sine x over cos x, and then when I multiply, I get sine squared x over cos x. The same thing on both sides. We're done. We've shown that the left side and right side are equal. Now, on the diploma exam, if you have a trig identity to do, and there have been on there, you have to make a statement at the end. You have to say left side equals right side. That's one option. Another option is what's known as the tombstone symbol. I'm not sure why they call it that, but basically it's a box that's colored in. If we look in Google for the symbol, let's put one more in here for proofs. So there's the definition. In mathematics, the tombstone, I'm thinking that's a Greek word, halmos, maybe, end of proof, or QED. So it's a box, or it could be colored in or not, as it says there. It's a symbol used to denote the end of the proof in place of the traditional abbreviation QED, which is a Latin phrase, meaning that you demonstrated what you were supposed to do. So you can use the tombstone symbol at the end if you want, or you can say left side equals right side. But on the diploma exam, this is something that is required. To get full marks on a proof, you have to either have that statement at the end or the tombstone symbol. Yeah. Yep. QED works as well, you betcha. If you want to really impress your marker that you know Latin, QED. So yes, you absolutely could. Okay. Part D, what are the restrictions on x? This is another way of asking for the non-permissive values, right? Our non-permissive values come when you try and divide by 0. So any value of x that gives a denominator of 0 will be non-permissive. So you need to look to see where your denominators occur. And if I look back in part C, cos x is a denominator on the left side as well as on the right side. Because when you change the tangent to sine over cos, you also get a denominator of cosine x. So our restrictions here come from the fact that cosine x cannot equal 0. Cosine x. But we want to state the restrictions in terms of x. And so we want to know where on the unit circle is the cosine 0. So let's use the unit circle and let's put the coordinates at the end of each axis there. Right? Those are the coordinates at the end of each axis on the unit circle. Cosine is the x value, and it equals 0 there at 90 degrees and down at the bottom at 270 degrees. So our restrictions on x between 0 and 2 pi would be 90 and 270, or pi on 2 and 3 pi on 2. However, we're not just going to worry about one turn of the unit circle. When we state our restrictions, we're going to state all restrictions from negative infinity to positive infinity. So we can say that x cannot equal pi on 2 plus n pi, where n is an element of integers. Right? We use this same notation when we solve general solutions, found general solutions for trig equations. So we're going to use the same thing to state our restrictions. We say x cannot equal pi on 2 plus n pi, where n is an element of integers. So there's the restrictions on x. So we will do a little bit more practice with showing that a statement is probably an identity for specific values of x. We'll use our graphing calculator to say that the statement is probably an identity, but the only way to know for sure is by proving it algebraically, which we did in part C. And that's what we're going to spend the bulk of the time on in this section, okay, as well as doing the restrictions. All right, so on the next page, we have a different statement. Sine x over tan x equals cos x. This time they want us to show that it is true for pi on 6 radians. So the left side will be sine of pi on 6 divided by tangent of pi on 6. The right side will just be cosine of pi on 6. So again, where is pi on 6 on the unit circle? It's close to 0. The coordinates there are root 3 over 2, comma, a half, and the tangent was root 3 over 3. It was 1 over root 3 that we rationalized became root 3 over 3. The sine of pi on 6, the sine is the y value, that's a half, divided by root 3 over 3, the tangent of pi on 6. So to divide by a fraction, you multiply by the reciprocal, and that gives us 3 over 2 root 3. And then if I rationalize this by multiplying top and bottom by root 3, we'll get 2 root 3 over 2 times 3, which is 6, or root 3 over 2, which is what the cosine of pi on 6 is. That's the x value at the point. So we've shown that the statement is true when x is pi on 6. We've shown that. To show that it is probably an identity, we can use our graphing calculator. The left side will go into y1, sine x over tan x. Got to close the bracket after the sine x, and then divide that by tan x. The right side is simply cosine x. So because the right side is cosine x, this graph will only go up to 1 and down to -1. We don't need to change our windows. I'll keep them the same, but it's just going to be a little bit scrunched together if you want. It happened fast. It drew the first equation in blue, then the second one over top of it, covered it up completely. So this shows that this statement probably is an identity. But the word probably is used because it's only showing that it's true between -360 and +360. Those are the windows that we had set. It's possible there's a spot somewhere outside that domain where they're not the same. And that is the reason why, to prove that it is an identity, we have to use the algebraic approach. We need to show that sine x divided by tan x is equal to cosine x. So, remember our hints. If there's no powers, put everything in terms of sine and cos. So I change the tan x to sine x over cos x. And to divide by a fraction, we multiply by the reciprocal. So it'll be sine x over 1 times cos x over sine x. The sine x's will cancel, and we're left with cos x. Two simple steps. Change the tangent to sine over cos, and then we multiply by the reciprocal and cancel. Pretty straightforward. Right? To find our restrictions, again, we need to look to see where there's any denominators, and the only place there's a denominator is from the tangent. And actually, it is from the tangent, but it's not just where cos x equals 0. And here's the reason why. Tangent is sine over cos. You see, if the sine x that's above the cos x equals 0, if this sine x that I just circled above the cos x equals 0, 0 divided by cos x will be 0, and then it's asking us to divide sine x by 0. So in this case, not only is cosine x giving us a restriction, but also sine x. Again, if the sine x that I've circled here in blue is 0, it doesn't matter what the bottom is, 0 divided by anything is 0. That makes this whole thing 0 that you'd be dividing sine x by, and you can't divide sine x by 0. So in this case, neither sine x nor cos x can equal 0. And now our restrictions are every multiple of pi on 2. At 0, that's where sine equals 0. At pi on 2, that's where cos equals 0. At pi, that's back where sine equals 0. At 3 pi on 2, that's where cosine equals 0, and it just continues like that. Now, you can verify these by using your graphing calculator. So I'm going to go into trace, and I want to be on the equation sine x over tan x, which I am. That was the first equation. That's what's displayed at the very top of my viewing window. The right side is just cosine x, and there are no restrictions from that. Okay, so I'm in the trace mode. I'm on the right equation that I want to do. My mode in my calculator is in degrees. So now I have to put them in degrees. But if I let x equals 0 and go enter, notice there is no y value displayed. That means x equals 0 is a non-permissive value. You don't get an answer for y when x is 0. If I let x equal 90 and hit enter, again, no y value is displayed. That shows that 90 degrees is also a non-permissive value. 180, no y value. That's a non-permissive value. Negative 90, no y value. Negative 270, no y value. So you can use the graphing calculator to verify your non-permissive values. We said in radians that x cannot equal n pi on 2. We can also say it in degrees. X cannot equal 90 n degrees. It didn't tell us what mode to use, so you can use either. Right, my calculator, because of the windows I chose and the mode I was in, it was in degrees. And that's what we use to check. Okay, but this is an or, right, depending on what mode you're using. So most of the time we're going to be asked to prove these statements algebraically by using other known identities and those tricks, those hints that we've talked about. And again, they are, if there are no powers, put everything in terms of sine and cos. If there are powers, especially squareds, look to the Pythagorean identities. If you have powers greater than 2, you might have to factor. And that's what you're going to have to do for this one, because that second term on the left side is sine cubed x. But there's a factor of sine x from the first term, so we can factor out a common factor of sine x here. There's a common factor of sine x. To get what's inside the brackets, you'll divide each term by sine x. So I'll just leave you with cos squared x from the first term. And the second term, sine cubed x divided by sine x, will give us sine squared x. So I took out a common factor of sine x. That's what I'm left with. What does cos squared x plus sine squared x equal? 1. That's that Pythagorean identity. So this is the same thing then as sine x times 1, or sine x, which if you go 1 over cosecant, that is sine x. We're done. Not that difficult, right? Some of you might have looked at that sine cubed x and your heart might have palpitated a little bit, felt a little sweaty in the palms. But again, a couple simple steps. Most of them are this easy. A couple simple steps. Okay? This next one will take a few more than a couple steps, but it's not rocket science what we're going to be doing. We're going to follow the hints that we were given before to prove that this is an identity. And then also it also wants us to talk about our non-permissive values. That's the values of A where the identity is undefined. Another way of asking for the non-permissive values. So if we go to our hints, there's no powers here. So that means we probably want to put everything in terms of sine and cos. And that's what I'm going to do. So the left side is sine A plus tan A, which is sine A over cos A. And that's all divided by 1 plus cosine A. And that should equal 1 over cotan A, which is tangent A. 1 over cotan, that's another way of saying the reciprocal of tan. The reciprocal of tan, 1 over cotan is another way of saying the reciprocal of cotan. The reciprocal of cotan is tan. So that's what the right side is. We need to get the same thing on the left side. And we might get tan A on the left, or we might get sine A over cos A on the left, but that's the same as tan A. But we need to work down the left side, which is the more complicated one, so that we can get it to tangent A. And as I said, this one's going to take a few more steps, but it's not rocket science. It's not anything we haven't seen before. This sine A is sine A over 1. And we need to add it to a fraction, sine A over cos A. So we need a common denominator to do that. So on the top, the common denominator will be cosine A. I need to multiply top and bottom by cosine A for that first term. Okay, times cosine A times the sine A. I'm multiplying top and bottom by cosine A. So this first term will be cosine A times sine A plus the sine A. Right? This second term already had our denominator of cosine A, so that didn't change. And that's all divided by 1 plus cosine A. So in this step, I just got a common denominator and added those two terms together on the top left. Okay, so this is the expression that I have right now. I need to show that that is equal to tangent of A. If I look at the numerator here, I can factor out a common factor of sine A. So that's what I'm going to do. common factor of sine A will give me cos A plus 1. And that's all divided by cosine of A. And that is divided by 1 plus cosine A, or 1 plus cosine A over 1. And this should all equal tan A. Any questions so far? When you divide by a fraction, you can do by multiplying by the reciprocal. So that's our next step. I multiplied by the reciprocal. And now, cos A plus 1 is the same as 1 plus cos A. I can divide top and bottom by cos A plus 1, which is the same as 1 plus cos A. When you divide something by itself, you'll get 1's there. So we have sine A times 1, which is sine A, over cos A times 1, which is cos A, and that is equal to tangent A. Tangent A is sine A over cos A. So we're done.
So in the black, that's just after the president, right? So you where did the plus one go on the denominator?
This 1 plus cos A?
Yeah, so you have to have everything back to the black next, right?
Yep.
And so where
1 plus cos A. If I circle it, let me use a different color here. The 1 plus cos A over 1 is right there. I just wrote it with a division symbol instead of a line separating them. I just wrote it with a division symbol. We good? All right. So yeah, this one took a few more steps. Agreed. But it's not rocket science. It's not anything we've never done before. Any mathematical steps that we haven't used in the past. Okay. Now, what about the restrictions? So, if we look at this, we've got a denominator from tan A, sine A over cos A. So cos A can't equal 0. This is not the same as the previous example, meaning that tangent became sine over cos. In this case, it doesn't matter that sine A equals 0 for the left side. Because when sine A, and when I'm talking about sine A, let me circle which term I'm looking at, or which part I'm looking at right there. When that equals 0, the second term will become 0. It'll be 0 over whatever cosine A works out to. But that's okay because you're adding it to sine A over 1. So adding 0 to something is fine. You just can't divide by 0. So from the left side, the only restriction we have right now is that cosine of A can't equal 0. But I've also got a denominator underneath here. And let me circle, I'm talking about the 1 plus cos A. That's a denominator. So that can't equal 0 either. 1 plus cos A cannot equal 0. So cos A cannot equal negative 1. When you take that 1 plus cos A not equal 0 and you get the cos A by itself by subtracting 1 from both sides, that's what you get. Okay, but let's look at the right side. The right side is 1 over cotan A. Now, it's true that that is the same as tangent of A. However, if you change the cotan, and let me circle that right now so you see what I'm talking about. If you change that cotan to cos over sine, which it is, that means neither cos nor sine can be 0. because cotan could be written as a rational expression, cos over sine. And because of that, neither cos nor sine can equal 0. Because either way, you'd be dividing 1 by 0. Can't happen. So the only thing we need to add here now is to say that sine of A cannot equal 0. So cos A and sine A, they will equal 0 at every multiple of 90 degrees. Cos A can't equal negative 1. That's at 270 degrees, which is a multiple of 90 degrees. So our restrictions here, again, is that A cannot equal every multiple of 90 degrees, or every multiple of pi on 2 radians. Okay? And you could put this in your graphing calculator to see that. Okay? If you wanted to, you can use the graphing calculator to check non-permissive values. So I'm going to use brackets here. I got sine x plus tan x. I've kept that all together as one term, and that's divided by, in brackets, 1 plus cosine x. And that should equal 1 divided by cotan x. Now, we don't have a cotan button on our calculator, so instead, I will use the fact that cotan is cos over sine. And I've kept that cos over sine x in a separate set of brackets to keep it together. I put times there. It should be divided by. There we go. So, I'm graphing them. If I go into the trace mode and I let x equal 0, notice that it does give me a y value of 0. All that means, though, is that the point 0, 0 is on the first equation. But if I go to the second equation by using the down arrow key, x equals 0, there is no y value returned. So that shows that 0 is a non-permissive value for the right side, which means it's a non-permissive value for the entire identity. If I let x equal 90, no value returned. I let x equal 180, no value returned. Negative 90, negative 270, no values returned. Okay, so we've just proven or shown that our stated non-permissive values are correct. Okay, so now we want to prove this one. We've got some squareds there. So that tells me to look at the Pythagorean identities. So let's open up the formula sheet here. There we go. So there's our Pythagorean identities there. We've got secant squared x on top and secant squared x minus 1 on the bottom. If I look at these Pythagorean identities, I'm going to focus in on this one right here. This is an identity. It is true. I showed you before where it came from. It is true. It came from the Pythagorean identity above. And we saw where that one came from. And it's also true. once we know that an identity or a statement is an identity, we are allowed to move things around. We've been doing that using that first Pythagorean identity. We did it once today already. We said that sine squared theta was 1 minus cos squared theta. We can do the same thing with the second identity, meaning that tan squared theta is equal to sec squared theta minus 1. If you take that identity that I circled in blue and subtract 1 from both sides, that's what you get. So sec squared theta minus 1 is equal to tan squared theta. This sec squared x minus 1 is equal to tan squared x. So I've got sec squared x divided by tan squared x. Because sec squared x minus 1, we just saw, is equal to tan squared x. So we need to get that to be cosecant squared x, or 1 over sine squared x, because that's what cosecant squared x is, 1 over sine squared x. So the next thing I might do here is I'll put these two parts into primary trig ratios. Secant is 1 over cos, and that's divided by tangent, which is sine squared over cos squared. And then if I continue over here, the right side is cosec squared x. On the left side, I'm dividing one fraction by another. We know that we can divide fractions by multiplying by the reciprocal. I'm going to do that. So I can divide top and bottom by cos squared x now, and we're left with 1 over sine squared x, which is what cosecant is. And we're done. We've shown that the left side equals the right side. With this last one, I didn't write it in there. We can write our QED, or our tombstone, or our left side equals right side. It doesn't matter. So 1, 2, 3, 4 steps. Simple steps, eh? Nothing really complicated. Use those hints. Try something. If it doesn't work, you try something else. You will never be given one that is not provable. If you're asked to prove an identity, it can be done. Some take 2 simple steps. This one took 4 simple steps. Some, like the one above, took a few more steps. Took a bit more room, but there was nothing really complicated about it, except that it took a few more steps. You try something. If it doesn't work, you try something else. Practice is what gets you good at this. Do the questions that are assigned. That one from last class, which was that row game, that was an important part of this. Working with other identities to get the same answer in both of them. That was just an introduction into this. Doing exactly the same stuff. Okay? So we're stopping there. It says do questions 1 through 4 for homework. So 1, 2, where it's on the first page. 3, 4 starts on that second page. And there's a couple more on the next page. So you won't have to do past question F on page 3. Next class, I'll show you some examples where you have to use conjugates, which is what the next questions are asking to do. Use conjugates, number 5. So you're just going to do 1 through 4. It's really important that you do these. put the answers on Google Classroom so you can check your answers. Use those hints though, okay? Most of them you'll be able to do in 2, 3, maybe 4 simple steps. Yes. Yeah. Okay.